Howdy, my name is Paul Terman, and I am with Texas A&M University on behalf of the LUX Dark Matter Collaboration. And I am coming to you recorded all the way down south in New Haven, Connecticut. That's right, New Haven, Connecticut, 45 minutes south of the University of Hartford, where we are being graciously virtually hosted. I'm here to talk to you about using the LUX detector to search for lightly ionizing particles, LIPs. Before I get started, please note that this talk has been pre-recorded. I won't be around for the question and answer session, but feel free to email me, and my email is provided in the slide. So these LIPs, also known as fractionally charged particles, are a theoretical concept where there's a particle with a charge less than that of an electron. They come about in a variety of dark matter related theories and non-dark matter theories. One example, for instance, is the magnetic monopole, where the monopole will get actually a slight electric charge as well under the Witten effect. In string theory, where there are multidimensional scenarios, LIPs also come out. And basically anywhere we have a hidden U1 dark sector, in the massless paraphoton case, that dark paraphoton will be the LIP. And that comes about from the kinetic mixing between the dark U1 and our U1, which is electromagnetism. LIPs can help solve problems with charge quantization within the standard model and explain other questions like the neutrality of the neutron. And of course, we also want to leave no stone unturned when we are looking for dark matter, because let's face it, we're starting to run out of room to look for WIPs. This slide shows the sensitivity of the LUX detector and the projected sensitivity of LUX's big brother, LZ, which is going to be going online rather soon. And it's looking in the parameter space of WIMPs, these favored dark matter candidate, where they are called the weakly interacting massive particle. And as you can see, as we push lower and lower in our sensitivity in this exclusion curve, we are going to be hitting this neutrino floor very soon. And basically at that point, we can't tell the difference between a neutrino and a WIMP, and then we're in real trouble. I want to give you a quick rundown of the LUX detector. It's a time projection chamber, a TPC, that was filled with 370 kilograms of xenon with a small gaseous region as well, mostly liquid, small gaseous region at the top. What happens is that an incident particle comes in, it smacks into that xenon. There's going to be an initial burst of light and scintillation. That's going to be what we call our S1 signal. At the same time, there are going to be ionized xenon and cast off electrons. Those electrons are then drifted to the gas-liquid interface via an applied electric field. They reach that interface, they are extracted into the gas region, where they produce additional scintillation, much larger signal, going to be called our S2. And it's the timing between the S1 and the S2 that allows us to find the depth, that Z dimension, in our TPC. It was located about a mile underground in the Homestake mine of South Dakota. And of course, it was optimized for WIMP dark matter searches, trying to look for that missing mass in the universe. But we can reanalyze it for other physics results as well, giving you a little bit more of a concept map of the TPC. We have our initial excitation, that's that scintillation from the S1. There is a contribution from recombination of ionized electrons recombining with xenon. We have the other electrons that are extracted to become our S2. Now, the important takeaway from this graph is that the energy reconstruction is a function of both properly tagging the S1 and the S2, because the gains that calibrate the energy output from S1 and S2 are very different. And it becomes very important to know the difference between those two things. There's also a component of energy that's lost to heat,
but LUX is not sensitive to that, and it is somewhat negligible, especially in electron recoils, which is what we would be looking for in our LIP search. Now, LUX has two PMT arrays, both above and below the main body of the detector, filled with 61 photomultiplier tubes. Each one of those tubes has a waveform output. As you can see here, each one of those PMTs contributes one little blip waveform here, 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 here. They are summed together to get the summed S1, as you see on this example, on the left. And we get the summed S2 on the right. Now, this is for a single scatter event. This was what we would expect from a WIMP. And when we get those summed waveforms, we can then toss that through our data processing framework, and we are able to get position information, energy, pulse classification, and a slew of other data. Now, what would a LIP look like? It would look very different than our WIMP signature. There are two different types of tracks, not single scatters, but multiple scatter tracks going through the detector. The first type is where we have a bunch of discrete hits along the detector, as we see on the left-hand side. And this can be a few dozen hits, dozens and dozens of hits. We've actually opened up the data processing framework to allow for up to 100 pulses to be found. Normally, our framework only allows for 10. This was a data analysis tweak that we made in order for the LIP analysis to be undertaken. Now, the second type of track that we could find is where we have this long, continuous, or mostly continuous block of ionization. This would be much similar to what we would see from a muon cutting through the detector. In order to simulate these LIPs, we've actually incorporated the JAONT4 monopole class into the LUX Sim simulation suite. What we do is we take that monopole class, we turn off the magnetic charge, we play with that electric charge that I had mentioned can come about from the Witten effect, and that allows us to toss that LIP into our detector. Well, simulate the LIP going through our detector. Now, here is a simulation of the first type of track. As you can see, we have our S1, which is actually mistagged as an else or unknown pulse. We've changed the framework a little bit to allow for an unknown or else pulse to be used in place of an S1 in terms of a properly tagged pulse. But we have our individual S2s all properly tagged. As you can see in the hit map here, this is the top PMT array where we have the hit. We see a nice straight line going across the detector. That's a very good simulation. Now let's take a look at the second type of track. Now this is a real muon that is cut through the detector, the through-going muon. As you can see, there is a lot of energy being released, and it's all continuous. Now, putting this in the data processing framework, we would get one long pulse. We would get no XY information because it's just one giant pulse. We would get no Z drift because there's no S1 and S2 to tag to each other to know the drift time. We would get no energy information, or at least no corrected energy information, and it would be a big problem. What we've done, we've chopped up those pulses. This is a simulated example of a long continuous pulse. And with pulse chopping, what we do is we first see, okay, is there a rather long pulse that is in an event in the detector? We say, okay, is that 40 microseconds? If so, is there a certain amount of structure there? Because we don't want to chop just anything that has a little bit of elevated baseline, perhaps, that could be going for a while. We want to make sure that there's a decent amount of structure, like we saw some of those delta rays coming out in the muon. We then go back to the first large pulse of the event. As you can see in this example, the S1 is disjoint from the main bulk ionization. But going back to that first large pulse allows us to find that S1. We cut off 500 nanoseconds for S1 timing, cut the rest of the physical extent of the detector, which is 320 microseconds, into 99 equal parts. And then we were able to toss that through our data processing framework and get all of those nice hits along the detector. Now, unfortunately, I don't have a whole bunch of time to go into all of the details of how we selected background versus signal, but there were three main methods that we've gone through. The first one is more of a traditional data selection cuts scenario where we take a test set of data of 15 days out of our 86 days. We assume that there is no data, there is no signal there at all, and then we make cuts to separate that non-signal data from our simulation that we are treating as signal. We then develop a region of interest on 6 parameters plus the notion of chopping, and we are able to get the orange simulation efficiency curve here. We then use those same parameters and we toss them into machine learning boosted decision tree. We get the purple line here. It's a little bit worse, but it can be looked at a lot as a verification of our previous data selection method. And then we open up the boosted decision tree to allow for all the information that we can give it, 71 parameters, and that gives us the green curve here where we see an improvement in simulation efficiency in all charges except for the 0.3 charge. But going down to 0.01 charge on the other side here, it's an improved efficiency. What does that mean for our flux? Well, it means that we are able to place new limits on flux. As you can see here, we have the 3 different methods with their different flux curves. The lower we are, the better, which means that we are currently beating out CDMS here and Majorana here with their more recent flux limits, and we are able to place limits in the range of 0.01 to 0.3 charge. And this is a great thing and a great accomplishment that we've been able to make. We haven't been able to beat out some of the very, very large detectors like Macro, who've gone out to very high charge, but we've really been able to hone in on this slightly smaller charge region. I thank you guys for joining me, and please note again, this has been pre-recorded. I won't be available for live questions, but please email me. And if you're interested in hearing more aspects of the LIP analysis, please join me at one of these other talks that I am either accepted to give or are hoping to be accepted to give. And I thank you again for your time. Take care. Be well.